Session, we have Lizhi Chen, who will be telling us about homology and homotopy complexity via systolic geometry. Take it away.
Thanks, Molly. So it's my great honor to share my research problem at this conference. So today I'm going to talk about some problems related to topological complexity and systolic geometry. I start from the definition of simplicial volume. Now let M be a closed orientable manifold of dimension, and we consider homology in real coefficients. Let M be the fundamental class, and we consider the cycle representing the fundamental class to be the sum I from what can lambda I, sigma I, and the lambda I are real numbers, and sigma I stands for a singular n simplex. We define the simplicial volume to be the ephemerum of the sum of the absolute value of lambda I, and the ephemerum will take over all real coefficient cycles representing the fundamental class. And for simplicial volume, we have the proportionality principle for hyperbolic manifolds. So the theorem is the simplicial volume is proportional to the hyperbolic volume. So from this theorem, we can see the simplicial volume can be considered as a topological version of hyperbolic volume. And now I introduce something in systolic geometry. Let M be a closed Riemannian n manifold. The homotopy 1 systole is defined to be the length of a shortest non-contractible loop. There is a theorem from Gromov. The homotopy 1 systole to the nth power is less than or equal to a constant c times the Riemannian volume. And this inequality holds for all essential closed n manifold. For here, the essential manifold, I do not want to reduce the definition, but I can give examples of closed essential manifolds. For example, the closed surface other than the two spheres is essential, and also n-dimensional torus, hyperbolic n manifolds. And all aspherical n-dimensional manifolds are essential, and also real projective n spaces. And in particular, all connected sums of aspherical n manifolds are essential. So according to the systolic inequality, we can define a topological invariant called the systolic volume. It is defined to be the ephemerum of the ratio volume of a homotopy 1 systole to the nth power. In terms of the systolic inequality, we know for all essential manifolds, the systolic volume is a positive constant. And moreover, Babenko proved for a closed orientable essential manifold, the systolic volume, it is a homotopy invariant. For the systolic volume redefined, I want to introduce some properties. In 2 dimensions, so I call it the systolic area. It is proved the systolic area for hyperbolic surface of genus G is approximately equal to J over log J squared when the genus is sufficiently large. And for here, we have a general theorem for the systolic volume. It can be considered as a generalization for the hyperbolic surface. So the theorem is, if we consider the closed n manifold with non-zero simplicial volume, then we have this relation between the systolic volume and the simplicial volume. So the relation is systolic volume is bounded below by constant Cn times simplicial volume over log simplicial volume to the nth power. And this theorem is one of the most important theorem in this area. So we call this area systolic geometry. and also it is one of the most difficult theorem in systolic geometry. This theorem is very important because so it tells us the systolic volume, it is such a topological invariant. It is related to the topological complexity. So the simplicial volume, it is a lower bound of the triangulation complexity. From this theorem, we see if the manifold is more complicated in topology, then the systolic volume should be large enough. I want to introduce one application of this theorem. We know for hyperbolic n manifolds, there is a finiteness theorem. When n is at least 4, the hyperbolic n manifold has this property. If we consider the hyperbolic volume is at most equal to a large enough constant k, then we only have finitely many such hyperbolic n manifolds. So combined with the finiteness theorem, Gromov's theorem tells us the following result. If we give a sequence of closed hyperbolic n manifolds, and in this sequence, every 2 hyperbolic n manifolds are not homomorphic to each other, then the systolic volume of this sequence of hyperbolic manifolds is going to infinity. So from here, Sparrow's theorem includes the dimension n equal to 3. This theory is so there are some special technique we need to deal with when n equal to 3. And for this theorem, it tells us a geometric finiteness in terms of systolic volume. So I mean, if we consider all hyperbolic n manifolds with the condition systolic volume is at most equal to C. C is a large enough positive constant, then there should be only finitely many such hyperbolic n manifolds. And next, I want to introduce the relation between homology complexity and systolic volume. There is one theorem proved by Gromov. If we consider a closed spherical manifold of dimension, then we have this relation between the Caspet number and the systolic volume. We have this inequality. The Caspet number has upper bound in terms of the systolic volume. So this theorem can be considered as it's a curvature-free version of Bethe number theorem. In differential geometry, Gromov also proved the upper bound of the Bethe number in terms of some curvature condition. My second part of the talk is related to embolic volume. So similar to systolic volume, the embolic volume is defined in terms of embolic inequality. Now let M be a Riemannian manifold of dimension n. We have Bézier's embolic inequality. So if M is compact, then the ejectivity radius to the n's is less than equal to a constant Cn times the volume of the manifold. This inequality is called embolic inequality. So the relation between the embolic inequality and the systolic inequality is if the manifold is also essential, then we should have the embolic inequality from the systolic inequality. So now I give a similar definition called embolic volume is defined to be the infimum of the ratio volume over the injectivity radius to the nth power. So for embolic volume, in fact, we have more nice properties. For example, for all compact N manifolds, we have embolic volume is a positive value. But for systolic volume, for example, if we consider the three manifolds S2 cross S1, the systolic volume is equal to 0. But for embolic volume, it's still positive. And for embolic volume, we have so the geometrical finiteness theorem. So for large enough positive number k, if we consider all compact N manifolds with embolic volume at most equal to k, and then there are only finitely many homotopy types. And in fact, for here, if we consider the homeomorphism types and the diffeomorphism types, we also have the finiteness theorem. So I think we should let N at least be 5. The dimension N should be at least 5. We have homeomorphism finiteness and diffeomorphism finiteness. So by the finiteness result, the set of embolic volume values is a discrete set. So embolic volume, if we consider to use the geometric functional to represent the topological complexity, the embolic volume should be a much better candidate. For here, since the ejectivity radius, it is less than or equal to 1/2 systolic, the homotopy 1 systole of M. So the embolic volume is always upper bound to the systolic volume. So Gromov's theorem relating systolic volume and simplicial volume has the following corollary. For closed connected N manifold with non-zero simplicial volume, the embolic volume has a lower bound in terms of the simplicial volume. And for batch numbers, I generalize Gromov's theorem for the embolic volume. So if we consider the compact manifold of dimension, the K's batch number has upper bound in terms of the embolic volume. So for here, the embolic volume it is greater than or equal to systolic volume. So Gromov's theorem relating systolic volume to the batch numbers has a direct corollary if the manifold M is aspherical. For here, I generalize the condition of aspherical to all compact manifolds of dimension N. So this is the reference and the end of my talk.
Wonderful, thank you. Great. Any questions for Lizhi? You can either unmute yourself, raise your hand, or put it in the chat, and I'll be happy to read it on your behalf. I have one question. So you have these two different types of volumes, and
yes.
What do you like? Is there a preference of when you use one over the other?
In my personal preference, I think the embolic volume should be a much better candidate because so for here, when we consider embolic volume, we only need to consider all compact manifolds. But for systolic volume, so for example, for S2 cross S1, the systolic volume is equal to 0. And also, I think for embolic volume, it has nicer properties. For example, we already know the such values for embolic volume is discrete. So this is a result from the differential geometry.
Great, thank you.